My name is Morell, and I'm a PhD student in the Autonomous Vehicle Systems Laboratory. My advisor and co-author on this paper is Dr. Hans-Peter Schaub. Today I'll be talking about our work on expanded back-substitution dynamics modeling for branched force and torque-based spacecraft components. First, some motivation on why we're interested in doing this expansion to the back-substitution method is because currently the back-substitution method works with a classic spacecraft architecture, which we see on the left here. That is a single rigid central hub to our spacecraft with its translational and rotational states, and then some number of components such as solar panels, reaction wheels, and thrusters, all attached directly to the central hub, or in other words, what we would refer to as being attached in parallel to this central hub. Now, what we see on the right are what I'll be referring to as modern architectures, some more ambitious vehicles that have these components no longer under the assumption of being attached in parallel to our hub. So for example, in the top right-hand corner here with Astroscale's Lexi spacecraft, we see thruster arms. So now instead of being attached directly to that central body, our thrusters have these 2 degree of freedom Revolute robotic arms between them and the central hub. We also see 4 docking arms on Astroscale's Lexi spacecraft, each of those having 1 translational and rotational degree of freedom. And now when they're grappled onto another vehicle, we'll be experiencing external forces and torques. And then in the bottom right-hand corner, we see Northrop Grumman's current mission architecture for on-orbit servicing, which has an entire secondary hub with its own position and attitude states, multi-degree of freedom solar panels, its own thruster arm. So we can see how we're seeing some more complex dynamical stacking on our vehicles. Another way we can think of this or look at this is by the dynamical topology of what we're trying to model. So here we see for our classic spacecraft architecture that central hub in the middle, and then the components, these dynamical effects all attached in parallel around it. Our thrusters, solar panels, reaction wheels. I'll also start making a distinction here between what type of dynamical effects we're considering. So those will be state effectors. These are dynamical components with some type of state coupled with the spacecraft's equations of motion that we need to consider. Think the rotational states of a solar panel that is able to gimbal about an axis, or reaction wheels, or think about translational degrees of freedom with associated states on a robotic arm. And then what I show in blue here or what I'll refer to as dynamic effectors. These could be components such as thrusters or a grappling end effector that are going to just be contributing forces and torques to whatever their parent body is. And this also includes dynamical effects. You can think solar radiation pressure, gravity, drag. These type of dynamical effects, along with things like thrusters, are not having explicit states coupled with our spacecraft's equations of motion, and will just be sending contributing forces and torques to the equations of motion. Why this is significant is what we look at with the topology of some of these more complex modern architectures that I was showing on the last slide. So now thinking about that robotic end effector, but with some number degree of freedom robotic arm between it and the hub. Same thing for our thrusting arms. We could have 1 or more thrusters on any number of segments between the hub and the end of the robotic arm. And as I was mentioning, dynamical effects as well. So especially for some of these larger rollout solar arrays that are being developed, especially wanting to consider solar radiation pressure, drag, things that are proportional to that surface area of these. And this arriving at our modern architecture. We'll also take a look at yet another way to represent our spacecraft here, just to come up with some common mathematical notation that we'll be using. We have an inertial frame, N, and then our hub, again shown in gray here, has a body fixed frame, B, on it. So we'll be referring to our hub states, translational and angular acceleration, as this R double dot and omega dot. We also have these several components, otherwise referred to as effectors, on our spacecraft. Here we see in the bottom left a sloshing fuel tank, as well as some solar panels flexing. And we'll just generalize any components with states to be propagated on our spacecraft as this alpha double dot. And now the historical assumptions of the back-substitution method are 1, that all these bodies are rigid, and 2, that all these components are connected directly to the hub in parallel. As we've shown in the past couple slides, that's the assumption in this work that we are breaking, but for the better. So a quick summary on why this is significant is just looking at the mathematics behind the back-substitution method. The main advantage that we use for our gains in computational efficiency and modularity in the back-substitution method is that when we form our mass matrix, we organize our equations of motion in such a way that these cross-component contributions are all zero. So what we want to do is preserve that so that we can still maintain this computational efficiency of the back-substitution method, as well as its modularity, by just augmenting dynamic effectors being attached to state effectors, such that what we're actually only changing is what happens on the right-hand side of this equation, and not altering the fact that these cross-component contributions remain zero. This is now to say that we could be modeling some of these more complex components using the back-substitution method, as long as we make sure that those cross-component contributions are zero, but it would have to look like this. You would have to derive custom analytical equations of motion for each specific combination of dynamic effectors on state effectors. So think docking arm with a specific number of degrees of freedom and type of end effector, thruster arms exactly on which segments and where we're having those thrusters attached along the arm, or what components or dynamical effects we want applied to our solar panel. And what we're working to do here is remove this, maintaining bassless modularity so that we can interchangeably have these swapped in and out as you're going through the design of your spacecraft. Here's a look under the hood into the bassless simulation framework, which is the simulation framework long developed by the AVS laboratory and what we're using as a test bed to implement these changes. And what we see now is the traditional effector setup, where you have your spacecraft, that central body, and then a downstream effector that you want to attach to it. You'd either call add state effector or add dynamic effector to attach that dynamical effect or component to our spacecraft. The spacecraft registers its states with the dynamic parameter manager. That way, anytime this downstream effector wants to know where its parent body is or how it is moving, it can link in those states and know that information. And then whenever that downstream effector has dynamical contributions to contribute to the spacecraft's equations of motion, if it's a state effector, it'll call this update contributions to send those. And if it's a dynamic effector, it'll call this compute force torque method to send those forces and torques to its parent body. What we are augmenting is kind of adding a second loop underneath this, where now a downstream effector already attached to the spacecraft, some intermediate body, can call add dynamic effector to add dynamic effectors to itself. It registers its properties with the dynamic parameter manager. That way, now this branched effector can know where its parent body is and how it's moving by linking in those properties if it would like. And then we can also have that downstream effector call compute force torque to contribute its forces and torques to its now parent effector instead of the spacecraft being the parent. We've also worked this out in much more detail in the paper, which I would encourage you to read if you're interested in the mathematics behind it. But just at a high level here, I want to show you what we're moving around within these to achieve these gains. So we see the total spacecraft translational equation of motion and rotational equations of motion, and then our generalized effector equation of motion that would be specific to each state of our effector. What we're doing is effectively moving these forces and torques that would normally be sent by dynamic effectors to this submitted force and torque in the total spacecraft equation of motions, and redistributing it out into the effector equation of motion such that it is then also added in the same magnitude to our translational equations of motion, rotational equations of motion for the total spacecraft, but with some considerations, more realistic effects that we'll now look into on these next slides. Here's that workout for a 1 degree of freedom rotating arm. So we see summing that force and torque across any dynamic effectors attached, and then these need to be implemented specifically to each state effector depending on how that state effector can move. So here, knowing that our state effector is a 1 degree freedom rotating arm, we have to normalize these torques and forces based on the direction that arm can move. And here's what I was alluding to just a minute ago as far as the realism that we gain from this. So what I show in the gold line here is what I'm referring to as hub-excited flexing. So this is having the thruster attached to this 1 degree of freedom gimbaled arm in the traditional way we would do in basilisk, using the back-substitution method, where when that thruster fires, it sends its forces and torques to the hub. The hub of our spacecraft accelerates, and then with flexing allowed in this arm, we see it deflect, lagging behind our central hub. But in a more realistic way, what we're now modeling and calling platform excited flexing here is that force that is generated by the thruster is sent directly to its parent body, the thruster arm. That arm accelerates, and it's rather the hub that starts to lag behind it. So we see both a opposite direction in the deflection of our robotic arm in the appropriate direction that it should be, with the thruster firing directly on it. And then we also see a larger magnitude of that deflection, knowing that, as is the case here and likely will always be, that the inertia of that arm is smaller than that of our spacecraft. And we see on the right here just the angle rate associated with this deflection, also showing opposite direction and larger magnitude. Here we also studied the hub states of our spacecraft. So we see the rotational states here. Effectively no perceived difference in the attitude, but if you look at the transient periods for our starting and ending of thrusting in the angular velocity, that larger deflection, we see a larger deviation from the hub-excited behavior on our hub. And we also studied the translational states. So we can see, especially with these, over just this 30-second initial time period, already a drift as we see divergence between the motion under our hub-excited versus platform-excited flexing. We've also been working this out for higher degree of freedom intermediate bodies, in this case a 2 degree of freedom gimbaled arm, now with the thruster on the second segment. And again, we're seeing our expected flexing behavior here in the deflection and deflection rates of our robotic arm. And this is to allude to what we're trying to fill out in totality using the bassless simulation framework. In the top, the x-axis here, potential child effectors, and then their parents listed on the y-axis. So wanting to attach these dynamic effectors to our state effectors. What we show in yellow is the total configuration space that we want to fill out. What is shown in red is what we are not actively seeking at the moment to do. And then this bottom row here, prescribed motion, shown in orange, will eventually have the ability to add any of these effectors onto it, but I'll have to defer you and recommend go looking at work by my colleague Leah Kiner if you want to learn more about that. So in conclusion, we're doing an alteration of the back-substitution method, surmounting a previous limitation where modular branching of components could not occur. We're achieving a more accurate flexing behavior with component-excited flexing, and this is greatly increasing the variety of spacecraft architectures that could easily be modeled using a back-substitution framework. I think some interesting next steps to this work would be creating a bassless interface for controlling thruster clusters across multiple intermediate bodies. You can imagine that normally you would request from your thruster cluster some force and torque that you want exerted on the spacecraft, assuming that that cluster is always going to be mounted in the same way on your central body. But now with thruster arms and these thrusters spread across our spacecraft, we'll need some more intelligent controllers to consider where are those thrusters currently when deciding who should fire and when to get a desired force and torque output across the total vehicle. I also think it would be interesting to expand analysis at the controls level and study the differences in resulting motion or resonance analysis when we have pulse control of those thrusters, while now mounted on these larger robotic arms and potentially subject to more resonance interference. Thank you so much for listening, and please feel free to reach out via email if you have any questions. You can explore the paper at hanspeterschaub.info under the conference papers section. And if you'd like to check out the code and some of the scenarios that we're working on implementing this in Basilisk, please refer to our GitHub. I'd also like to acknowledge and thank the support by my NASA NST JRO grant, and thank you so much for listening.